All right. Okay. So we are going to start with module 6 tonight. It's also quite a big module. Yeah. So I, I think with this one, I'm pretty much going to dive straight into examples. It is a bit, So I would, So you guys should go read the theory about rectifiers. Please go read this. But the gist of this, basically, is that you guys need to know with a half-wave rectifier, you're only rectifying half of your input waveform or of your supply waveform. So essentially, you're going to have half the RMS voltage on the output than what you're going to have with a full-wave rectifier. Right, so that's kind of important, or you're going to have half the average voltage. That's also a valid statement there. So so that is without having capacitor and inductor filters in the circuit. If you however add filters to the circuit, that changes things a little bit. You can also have transformers, but transformers are very straightforward to deal with. This is just pretty much N3 and N4 work again. If we take a look at these equations here, so I want to warn you guys, because I do see people using these equations sometimes for circuits that are filtered or rectifier circuits that are filtered. These are for unfiltered circuits, right? So no capacitor, capacitor or inductor filter for these formulas, right? So if you're going to use those formulas for a circuit that has a filter, you are definitely going to get the wrong answers, right? And so that's for your average voltage. And then for your ripple voltage, this ripple voltage, there's also formulas for this. This still is without filters. Okay. Right, so ripple voltage is not just that ripple there. If you don't have a filter, then the whole thing becomes your ripple voltage, right? So the whole signal. Okay, so that's just something that you guys need to keep in mind here. And then you have your peak inverse rating. So another thing that we need to keep in mind. That's basically just the voltage that your diodes need to be able to block, which is usually your supply voltage. For this subject, for some reason, full wave rectifiers need to block 2 times the maximum supply voltage. I actually don't fully agree with that, but for this subject, you guys need to know that. Okay, right. So sorry if I'm like blasting through this a little bit. I feel like we should maybe do more examples on this then. That's what I'm going to get to now. Right. So unfiltered circuit basically is going to look like this, right? So you're just going to have a resistive load, you're going to have your rectifier bridge, or in the case of a center tap transformer, full. Okay, so unnecessary, but in any case, with the center tap transformer rectifier circuit, similar thing. You're still going to have a very similar output, but as you can see, it's pretty much just your diodes and your load. Same with the half-wave rectifier. Now, if we take a look at, so this is now where the filter circuits come in. So the goal of the filter circuits is basically to reduce your ripple, right? So basically to reduce your ripple and to increase your average voltage. So so essentially this is then going to either take the form of a capacitor in parallel with your load, or so essentially what the capacitor is going to do is it's going to store charge and then discharge during the time that your waveform is going lower, right? So there are a few things that we also need to keep in mind here with the filter circuits. So remember, components like capacitors and inductors are frequency dependent, so that's also going to have an influence on how we calculate ripple for half-wave rectifiers versus full-wave rectifiers. So I don't know if you guys noticed this already. In a half-wave rectifier, our frequency or our ripple frequency on the output is the same as our input frequency from our supply. Whereby with a full-wave rectifier, let me quickly go over 2.1. Guys will see that the pretty much double our ripple frequency. That does have an advantage over, actually quite a big advantage over half-wave rectification, in that you need a smaller capacitor to do the same filtering. Right. Okay, so yeah, so here are the formulas that we have for half-wave rectification. So take note of the frequency there. You guys will see with full wave rectification, that's going to be 4 times F times C. So that 4 is to account for the doubling in frequency. So the frequency that we fill in there, that's the frequency of your supply, not your output frequency. And your DC current, or your average current, that's just your average voltage divided by your load resistance. And then your RMS value for your ripple. So basically the RMS value for that peak-to-peak voltage there. That's then just going to be your peak-to-peak value divided by 2 times square root 3. So essentially where this comes from is it's basically estimated as a triangular wave. So yeah, and how you calculate the RMS for a triangular waveform is by dividing by square root 3. And yeah, so you can also substitute the peak-to-peak voltage here with IDC over FC as well. Again, you guys will see with a full wave rectifier that 2 is going to change to a 4 to account for the doubling in frequency. And then you also have your ripple factor. So again, take a look at the frequency. That 2 is going to change into a 4 for a full wave rectifier. So again, just want to reiterate, the frequency is going to be your supply frequency. It's not going to be the ripple frequency. All right, so there are some disadvantages with capacitor filters. They have very limited current delivering capabilities. So they're not pretty good at delivering current. And yeah, so if you pull more current, yeah, so this is where the current delivering capabilities come in. So if your load pulls more current, that actually is going to increase the amount of ripple that you see. So if we go back to this formula here, so IDC is your average current. So if that goes up, so does your ripple RMS, so your ripple increases. So this thing starts getting worse at higher current. So your average voltage is going to go lower. Okay. So that also means your capacitor filter only doesn't have very good voltage regulation as well. So because, yeah, so increase in load current, you're also going to have a significant decrease in average voltage. Full wave rectification, not that much different from the half wave, except like I hammered on earlier, all the 2's here associated with the frequency are all going to change to 4's. Right, but essentially the formulas stay the same. Just we account now for the doubling in frequency on the output. Right, so pretty much the same procedure here. Then, yeah, so there are a few examples in the slides. I just realized I never made the slides downloadable. Do that. Okay, so yeah, so there are a few examples here in the slides. I'm not going to focus too much on them. You guys can go work through them. I'll do the exercises from the textbook as well. I think there's an exercise on each filter example. So I'm just going to quickly go through this. Again, you can also have RC filters. So to improve your capacitor filter a little bit, you can add a resistance series to your already existing capacitor filter and an extra capacitor. Right, so that decreases your ripple voltage even further, increasing your average voltage for a given load, improves your current delivering capability slightly as well. So there are the formulas associated with this. Cool. So you have half wave rectification and you have your full wave rectification. The calculations, however, for both full wave rectification and half wave rectification are pretty much the same. So you're going to have VDC prime or your average voltage prime. So VDC prime sits here across your load. So that's your load voltage, VDC prime. And VDC is your original output voltage after your first capacitor filter. So that's where that sits. Right, so that RS basically forms a voltage divider with RL for the DC voltages. Then your ripple voltage, because it's an AC voltage, it's pretty much just going to be dependent on the capacitors. And yeah, this should actually be RS. Yeah, that should be XC2, not, yeah, so specifically that second capacitor there at the end. And yeah, so what you need to keep, this is where the frequency part now comes in. So for half wave rectification, you use your normal formula for capacitive reactance. For full wave rectification, on the other hand, remember to double your frequency. Right, so that's where the 4 comes in. Right, so if your line frequency is 50 hertz, you just substitute the frequency of 50 hertz, and in the full wave rectification, that 4 already accounts for that doubling. So you don't have to fill in 100 hertz. What else is there? Okay, and then your ripple factor will then just basically be VR prime divided by VDC prime. So a new ripple factor. Yeah, so as you guys can see, the ripple factor is basically the ratio of ripple voltage to DC voltage. Okay, there's another example. I'll work through the examples in the text or the exercises in the textbook for us. Right, then you can also add an inductor instead of just a resistor here in that branch there. That's also going to change the formulas a bit. Kind of simplifies things a tad bit. VDC prime, again, going to calculate the same way. So that's going to sit there. And old VDC is going to sit there. And yeah, so you get the voltage division here due to the resistances. And your RMS ripple. Okay, so for a half wave rectifier, that's going to be 1 divided by 2 pi f squared multiplied by L multiplied by C multiplied by the old RMS ripple. And you're also going to have something similar for the full wave rectifier, but remember that 2 needs to now change into a 4 to account for the doubling in output frequency. Again, ripple factor, same formula here. So as you guys can see, there's a lot of reusing of elements in these equations. So if you learn one set of formulas, then the other set of formulas is very easy to adapt to. Okay, so yeah, so I know I went through this very quickly, but just want to see what else we have here. Okay, so then there's regulators. So regulators is pretty much mainly theory, except for the Zener diode has a bit of calculation there as well. I just want to quickly see. Okay, I think that's pretty much the only calculation stuff really. Okay, there's this as well, but this is pretty straightforward to go through. But I think what I'm going to do is I'm going to do a few examples on the rectifiers. So the rest of the stuff, I would recommend that you guys go read through this if we don't get back to this on regulators and Zener diodes. So yeah, don't have a lot of time to go through everything. This is exercise. Let me write it down here. Okay, so let's see what we have for this example. We're given a 220 volt 50 hertz supply. So this is actually an RMS voltage, so keep that in mind. Rated at 15, yeah, so rated at 15 amps, feeds a step down transformer with 220 windings on the primary side. We're told then should 10 volt be measured on the secondary side, then determine for the full wave as well as a half wave rectifier the average DC output voltage and ripple factor and the RMS secondary current. Okay. Okay, so the average DC output voltage, that's going to be pretty straightforward to calculate. So so you can do, I think let's do full wave rectifier. I'm going to leave half wave rectifier then for you guys to go and calculate. In fact, we can maybe infer some of the values already here. So if we take a look at full wave, I'm just going to do for the full wave here. So that's the average DC output voltage. So the 10 volts that we measure on the output of our secondary coils of our transformer. So we're not told whether this is a maximum or an RMS value. I'm going to assume it's an RMS value, seeing that it's not qualified. So that means the maximum value is then going to be square root 2 times 10 there. Right, so our DC voltage in this case is then going to be the maximum of our secondary voltage multiplied by 0.637, I believe. That 0.637 is equivalent to, if I remember correctly, is 2 over pi. That's actually where that comes from. Let me just make 100% sure for you guys. Yeah, that's actually where it comes from. Right, so you can use that 2 over pi if you want to. I'm just going to stick with what the textbook has. So that's then going to be square root 2 multiplied by 10 volts multiplied by 0.637. And that should give you, it's just going to give you over 9 volts, so 9.009 volts. I'm going to get there. Ripple factor. Okay, so for the ripple factor, we're pretty much going to need the ripple voltage for this. Yeah. Now that's actually, I know actually both textbooks have some issues. So the one that we're using actually explains some of the stuff much better, but then is quite bad at some things. Like there are a lot of typos, and I find that the information on, especially chapter 1 with the transistor amplifiers, the textbook that we're using does have small bits of information missing, and with rectifiers, there's also a bit of information missing on what the disadvantages are with voltage multipliers. Voltage multipliers not really good at delivering current. You get to a point where, so if you have multiple stages, you start getting diminishing returns, if I can put it that way. Sorry. And I think the other textbook is more lacking in more important areas of the content. So so I guess that's why the campus is still sticking with this textbook. But this textbook is also a bit more, I don't know. I think in the past when it was all hard copies, it was much more available as well. Okay. Any case, I just want to get the slides open here on another window so I can actually use the formulas, because I don't have these numbers memorized really. And usually you guys are going to get a formula sheet, so I'm sitting here trying to remember the stuff here off by heart. Okay, let's see. For the ripple factor here, so remember we don't have a filter here, so we need to use the equations here. That's applicable to not having a filter. Okay, so the formulas that we need to look at here are these ones here. Right, so because we're working with a full wave rectifier, we are going to use this formula here. And then ripple factor is then going to be an easy step from there. All right, so the full wave rectifier's ripple RMS, that's going to be 0.305 multiplied by the maximum voltage, which is again in this case going to be that square root 2 times 10. And this should give you a ripple here of ripple RMS of 4.313 volts. And that will then can then be used to calculate the ripple factor. Sorry, that's just going to be R. So basically the amount of ripple versus average voltage or DC voltage. You can actually express this as a percentage as well, so I forgot to mention that. That's then our ripple RMS divided by our DC voltage, which is then 9.009. That gives us a ripple factor of 0.478 or 0.479 rather, if you round it down, or yeah, if you round to the third decimal there. All right, so essentially what that means is 47.9% of our output voltage is ripple. So yeah, so you guys can see actually quite big there. So essentially what we're sitting with here is, so remember this is unfiltered, so our waveform is going to look something like this, or full wave rectifier. Now essentially what that RMS ripple is if we take the average, so if we say that's the average there, so which is going to be VDC, and we shifted that down as our zero, then we calculate what the RMS is of that and that. Right, so that's where the ripple RMS comes from. That's why it's such a weird value. But anyways, if we now, let's see, what we have now here is, let's just see, average DC voltage, RMS secondary current. Okay, so the RMS secondary current, so that's kind of not really a rectifier question, but we can go and calculate that. Do you have the voltage ratio? So V1 over V2 is equal to I2 over I1, and I1 is given to us as 15 amps. So we can go and actually calculate this. So I2 then going to be, yeah, so we're going to use the RMS values here. That's going to be I1 times V1 over V2. That's 15 amps multiplied by 220 divided by 10. That essentially becomes 15 times 22. And that's going to give you 330 amps. Which makes sense. You're going to have more current on your secondary side of your transformer than on your primary. Yeah, I believe for industrials in 5 and industrials in 4, I think it's the same author. So yeah, so that's why they have common problems. But the M5 textbook much less than the M4 textbook. And then you guys are going to get to industrials in 6, which is honestly the easiest of the 3, believe it or not. So yeah, so it's a bit of a break. Right, okay. Right, so let's take a look at using a filter circuit. I think let's take a look at using a capacitor filter, and then I think then let's go to the extreme and look at what happens if we use an LC filter. And then if we have enough time, actually maybe want to look at a xenodiode example as well. In fact, the exercise in the textbook has a bit of a mistake. I'm just looking here now for an exercise with both inductor and, or rather just a capacitor filter here. Okay, found one. Okay, so same exercise, just number 616. Just going to scroll down here. Okay. Okay, so this one is going to be a tad bit more involved. So here we are told it's a full wave bridge rectifier, but I would maybe urge you guys to go and try it as a half wave rectifier as well, just to challenge yourself a bit. Right, so let's just see what we're given here. So, so we're given the input to the transformer, which is 280 volts and 60 hertz. We're given the voltage across the secondary winding, which is 18 volts. Remember, this is still an RMS voltage. They're not qualifying it, so assume it to be an RMS voltage. Value of our load resistors 1.2 kilo ohms, and we have a load current of 15 milliamps. So we now need to use this information now to go and determine the following quantities. If we have 150 microfarad capacitor filter, and then separately for a 90 microfarad capacitor filter. Essentially, what this exercise is aiming for is to demonstrate the two capacitor sizes. So what happens if you increase your capacitor filters size? Now, I'm not going to do both. I mean, you can actually see from the formula. Let me maybe copy the formula in here, and then you guys can see for yourselves what will happen when the capacitance is increased. Let me just find that formula real quick. Yeah, okay, I think that's that is for the capacitor filter. Where am I now? Okay, in any case, do this. So we are working with a full wave rectifier, so I'm just going to copy that formula for us in. Actually, all the formulas, if I can. Maybe do that. I remember the fours in this case, if we were working with a half wave rectifier, would all be 2s. Right, so seeing that we're working with a full wave rectifier, remember half wave rectifier, those 4s will be 2s. Anyways, I'm going to take the 150 microfarad example and then just work with that. But you guys can see what is going to happen. Right, so if we increase the capacitance in our filter circuit, you guys will see that increasing that, it's going to make this component smaller. This component is your voltage peak to peak. In fact, you can actually see this in the other form of the equation, right? So that's your voltage peak to peak. That's going to be influenced there. So the bigger the capacitance, the smaller your voltage peak to peak is going to be. Right, so you can also see here in your ripple voltage calculation as well. Increase the capacitance, you're going to have less ripple for a given current. All right. So yeah, so let's quickly then calculate the values here. So I'm going to leave this 90 microfarad one. You guys can go do as homework, and then you can compare values with what we get here to what you get. But like I say, you can already see in the formulas, you can already predict what's going to happen. So if you're going to put in a smaller capacitor there, you're going to have more ripple. Okay. Okay, so for 6.1.6.1, oh, what a mouthful. Average value, that's then going to be your maximum voltage or peak value minus IDC over 4FC. Okay, so the maximum voltage here, that's going to be square root 2 times 18. Minus, what is IDC? That was given to us as 15 milliamps. So that's 0.015 or 15 times 10 to the minus 10 if you want to. Frequency is given to us as 60 hertz. And the capacitance, we're going to use the 150 microfarad example this time. Let's quickly calculate what this is going to give us. Okay, square root 2 multiplied by 18. Then minus that whole thing, 0.015. Okay, multiplied by 1,000,000 so long. And divide that by, or multiplied by 60, multiplied by, and if I calculate it correctly here, you should get 25.039, which is actually very close to the maximum value. So it means we're going to have a very small ripple factor here as well. Then the RMS, yeah, so the RMS value, yeah, so 6.1.6.2. Yeah, so I'm not too sure if they're referring here. Yeah, I think that's the ripple RMS, though they do ask it here, though. So this is what I mean with the textbook is sometimes a bit off here. In fact, I think this RMS and average value, this is your AC. So they're not very clear on what they want you to calculate there. But that could be either your input to your transformer that you're calculating there. So not really clear. So yeah, so I think let's just say we calculated 6.1.6.3 here. In fact, I haven't really seen in the exams the question asked in this weird way. They very rarely do the transformers, and if they do, they will explicitly say, okay, cool, calculate the average input voltage, calculate the RMS value of the input voltage. Right, so it's not like they're going to leave you in the dark. Let's see here. Okay, so we actually essentially went and calculated that now. So for the AC stuff, I'm not really going to focus on that because that is something you guys should know how to do by now. Then for 6164 is the RMS ripple. So let's keep with green here. Just make that a 4. Right, so we expect this value to be quite small now, seeing that this is actually quite close to what the maximum voltage is. Let's see, this RMS value, that's going to be IDC over 4 square root 3 times FC. $60 hertz, and our capacitance again is 150 microfarads. Okay, that's essentially 0.015 times 1,000,000. And then that divided by 4, divided by 60, divided by, let me just start over, I think I mistyped something here. Okay, divided by 4, divided by 60, divided by 150, and then finally divided by square root 3. So this is going to give you a ripple RMS of 0.241 volts, so 241 millivolts basically. Very, very small. And then your ripple percentage or your ripple factor. So ripple factor, that's going to be VR over VDC. So yeah, so in this case, they're asking a percentage, so you can just multiply that with 100. So this is then going to be 0.241 divided by 25.039. You guys can see that it's going to be a very small value, and that is just because our average voltage is very close to the maximum voltage, which is kind of what you want. Give you a very small ripple here. Yeah, this is gonna give you 0.8. It's just times 100 there. So that's gonna give you 0.86%. Which is less than, well, it's less than 1%. So that's actually quite good as power supplies go. Okay, so let's do maybe another example, maybe with the LC filter, which we could maybe use the same values here and do it, but I'm going to use an exercise from the textbook on this one. There's an RC filter, LC filter. Okay, 6110 as an LC filter. Take a look at that one. Okay, but I think for this one, seeing that we've done the full wave rectifier now twice, I'm going to do this one as a half wave rectifier. In fact, let me maybe copy the whole question because they ask here to do the drawing of your circuit that you're going to use. So they are letting you choose what to do here. What I would say would be good exercise is if you guys go and do this, do the other circuit on your own, that the one that we don't do here. So I'm going to do half wave rectification here. So you guys can go and see what happens with full wave rectification. So we have an LC filter that consists of an inductor that has a value of 1.4 henries. And a resistance of 120 ohms. So the resistance there. And the capacitor then has a value of 120 microfarad. And we have a load resistor with a value of 80 kilo ohms. And a voltage of 12 volts is then measured across the first capacitor. So that's actually our original VDC. And we have a ripple, original ripple of 6 volts. Okay, then our primary voltage is 180 volts, 50 hertz supply. That's not really, we're not really going to care about that in our calculations here. Right, so essentially what we need to go and calculate is our DC output voltage. So that's VDC prime. And our ripple factor, or our new ripple factor, we need to go calculate as well. So that's also going to need us to calculate VR prime as well. Okay, so VDC prime, that's actually quite a straightforward one to do. 6110.1. Right, so for VDC prime, so essentially you're going to ignore the reactive components, meaning the inductor and capacitor. They don't really care about the DC. They are more going to be impacted by the AC component, basically the ripple. So we can just use our resistances here as a voltage divider of VDC. And we want the voltage across the load, but we also have RS. Right. So VDC, that's 12 volts. RL, that's 80,000. That's saying RS plus RL is then going to be 80,120. That's going to give you, multiply that by 12, that's going to give you 11.982 volts. Right, so that's VDC prime, or your output average voltage. Next up is the ripple factor. So for that, we need to go calculate what the new ripple RMS is. And if I remember correctly, that's basically your old ripple RMS divided by. So we are working with a half-wave rectifier, so that's 2 times the frequency. Just make 100% sure on this. You know if pi is in the formula there. Yeah, pi is in the formula. So, okay, so 2 pi f. Let's do it like that. that squared times LC. Right, so for the capacitor, so for the resistor or RC filter, you're basically going to have just the voltage division due to the series resistor and the extra capacitor. Right, so then you have to calculate the capacitive reactance then in that case. But anyways, we have the inductor here as well, so things are going to change a little bit here. So so we are given this ripple voltage as 1.6, as then 2 times pi times 50. This time the frequency is 50 hertz. So guys, be careful, read your questions and make sure you're using the right frequencies. Even the exams, they sometimes use 50 and 60 hertz back and forth, so be careful. That is then 1.4 multiplied by 120 times 10 to the minus 6. Right, so this is actually not too bad. So that's 1.6 times a million divided by 0.4 divided by 120 and divided by that other whole thing, 2 times pi times 50, that whole thing squared. That should give you a ripple voltage in this case of 0.0964 volts. Right, so your new ripple factor now so that's going to be 0.096 divided by 11. Okay, that's nice that this happened. I hate when my laptop does that. That's then 11.982. And this is going to give you a ripple factor of 0.008. Or so if you have to do it as a percentage, that's 0.08%. All right, cool beans. Right, or actually 0.8% if you multiply with 100. I see that now. Okay. Right, you can actually, if you want to, you can actually see by how much your ripple factor actually improved if you go do this thing. So if you go with the original values, so 1.6 divided by 12. So this is your old ripple factor, 0.133, 13.3% ripple. So so that's actually a significant improvement in your ripple there. All right. Any questions? Right, Loden. Okay, I see nobody else asking or saying anything, so I'm gonna take it you guys are either doing okay or completely stunned. But what I can say is though, guys, just go through the slides through the examples. I also recommend if you guys can. I don't know if it's uploaded for you guys. I hope so. Otherwise, I'll have to probably do it. Old question papers. That's also a very good source of practice. Right, so I would recommend you guys go do that as well. All right. Okay, I think I think Luren, you're gonna see the rectifiers are pretty much it's the same. I think in M4 you guys do also do all the filter circuits, so that's pretty much a repeat of everything. I know the memos are sometimes wrong. I know actually of 1 and 5 paper where they did the AC calculations very wrong. I think the best that you can do there is to I'm trying to think here of a way that you guys can maybe contact me. But I usually the ticket system's a bit slow. But you guys can. There are ways to verify this, man. Just trying to figure out, try to remember there's actually stuff you guys can use. But yeah, anyways, you guys can email me. All right, guys, then have a good evening.